Picture a customer refund agent that has been running on a single support ticket for 9 continuous minutes. It looked up the order, decided a refund was warranted, and then got stuck. It is now caught in an infinite loop, retrying a database lookup. Along the way, it handed a research subagent the entire conversation history, leaking a different customer's personal data. The logs even show the model printing. Okay, I think I'm done here 4 separate times while it blindly continues to call tools. If you are taking the Anthropic Claude Certified Architect exam, the CCA-F, every one of these failures is a domain 1 question waiting to happen, and they all share a single root cause. The system is relying on the model's probabilistic guesswork to manage control flow rather than enforcing deterministic boundaries in the code. This diagram shows the required alternative, a hub and spoke architecture. A central coordinator manages the task and delegates strictly scoped work to isolated subagents. To move from our broken runaway loop to this clean design, you have to follow one strict rule. When a system fails, you remove the architectural root cause. You never bolt more infrastructure onto a design that is broken underneath. We are going to deconstruct this failing agent loop step by step and implement the 6 repair patterns required to pass domain 1. Mastering these 6 patterns is the actual difference between shipping a brittle prototype and deploying a secure enterprise-grade production system. The first failure in our autopsy is how the agent decides to finish its job. Right now, it runs a while true loop that searches the model's output text for a magic phrase like all done. Searching prose for a completion signal creates critical bugs. If the model says, I'm all done looking up the order, now let me process the refund, your substring filter matches immediately. The loop terminates mid-task, and the transaction is never finished. The repair ignores the text entirely. Instead, your control flow branches exclusively on the explicit stop reason provided by the API in the response payload. If the stop reason is tool use, you execute the requested tool, feed the result back into the context window, and let the model run another pass. If the stop reason is end turn, the model is finished. You halt the loop cleanly. Robust control flow is driven by deterministic API signals. The model's probabilistic prose is irrelevant to the application's execution state. The second failure involves how we handle subagents. Our central coordinator passed the entire running conversation history, including PII from a previous customer down to a researcher. This oversharing creates immediate privacy risks. It also degrades quality. Forcing a subagent to parse walls of irrelevant history increases the chance it gets distracted or loses the relevant signal in the noise. The fix is zero inheritance. A subagent inherits absolutely nothing by default. It must be initialized with a completely fresh context window. To spawn a subagent, you provide a tight, purpose-built prompt and a least privileged tool list, like read-only database access without refund permissions. The coordinator owns the decomposition of the complex task. The subagent merely executes the narrowly scoped piece of work it receives. Treating subagents as isolated, stateless workers enforces operational boundaries and prevents data breaches by design. Because context is strictly isolated, you have to choose how state moves between agents. For small, immediate inputs like an order ID, you pass that data directly within the spawning prompt of the subagent. For large artifacts like a 50-page returns policy, you pass the data through a shared file. Cramming that into the prompt wastes tokens and bloats the request. When the subagent finishes, its findings must be returned to the coordinator as machine-readable JSON inside the tool call result. Matching your handoff mechanism to the data's size and persistence keeps the multi-agent system performant. The third failure is the infinite retry. A subagent encountered a flaky database lookup and kept retrying indefinitely, burning API costs and hanging the system. You fix this by handling errors at the lowest capable level. You give the subagent a strict small local retry budget, usually just 2 or 3 attempts. If the budget is exhausted, the subagent escalates. It returns is error true, carrying the context of what it tried. Returning an error payload rather than crashing keeps the API loop alive. The coordinator catches it, routing to an alternative plan or a human agent. Bounded local retries paired with explicit escalation allow the system to fail gracefully without silently exhausting resources. The fourth failure involves financial safety. Our agent had a system prompt rule, never process a refund over 500, and occasionally the model ignored it. Prompts are probabilistic suggestions. They are not guarantees, which makes them unsuitable for enforcing security boundaries or financial limits. To create a hard guarantee, move the rule into your application code using a pre-tool use hook. Before the tool executes, the hook inspects the payload. If it sees an amount over 500, it issues a deny decision, blocking the transaction completely. A model can talk its way around a system prompt. It cannot bypass a hook, because the hook runs in your software, not in the model's reasoning. Any rule where a violation causes financial or security harm must be enforced entirely in deterministic code. Underpinning all these fixes is one law. The Claude API retains no memory between calls. It is completely stateless. Anthropic designs and documents Claude as a highly capable but stateless API tool. Every call is strictly independent. Every element of continuity, the history, the identity of the customer, the running state of the task, is something your application code must actively supply on every single request. It is dangerous to assume a model naturally remembers context from a previous turn. It does not. It is equally dangerous to assume a subagent implicitly knows what the parent coordinator knows. Designing for this inherent statelessness ensures your system stays resilient as it scales, and it is exactly the judgment the CCA-F rewards. Our architecture is now repaired. The loop terminates on precise API signals. Subagents are isolated. State moves deliberately, and hard limits are enforced in code. When taking the live CCA-F, you must be ready for the reflex distractor traps. The exam is designed to offer tempting but incorrect solutions. If an option suggests adding a routing classifier, strengthening the system prompt, or raising the retry ceiling to fix a failing loop, reject it. These distractors merely mask the symptoms of a poorly designed agent loop, rather than removing the cause. True architectural integrity means you always choose the fix that removes the broken underlying design. Mastering these architectural tools requires understanding the specific technical nuances of the Anthropic ecosystem. Subscribe to Insight Engine and follow us on LinkedIn, Substack, and Medium for technical deep dives into advanced AI patterns. And if your organization needs to build robust, deterministic LLM systems higher spillway, we engineer the agentic infrastructure that moves production metrics.